Hi there. In this lesson, we're going to explore some basic principles of theoretical probability. And in addition to that, we're also going to try to combine this idea of how likely some event is with this question of what's on the line, whether I'm right or wrong in guessing what the possible outcome of some probabilistic event is going to be. So our general point of orientation is that the unit we're in right now is talking about likely inferences. Sometimes we'll call these inductive inferences or inductive arguments as contrasted to deductive arguments. And we've been talking about our inductive arguments as the sorts of things that we want to make sure that we can slow our thinking down on. We know we're automatically going to kind of on a gut level do this sort of intuitive induction according to heuristics and biases that we have that are implicit and unconscious, but we'd like to, at least occasionally, if we're going to be rational, if we're going to be critical thinkers, we need to slow our thinking down and be a little bit more careful about how we're working through an inductive or a likely inference. And we've been identifying that with all kinds of inductive inferences. This goes for analogies and generalizations as well as statistical syllogisms, which is what we're looking at here. We have three kinds of concerns that we want to be paying attention to that will help us slow down our thinking. Some questions that we can ask that kind of pump the brakes on whatever kind of gut level biases I might intuitively be thinking in terms of moving from premises to conclusions. The first of these is a quantitative concern, this how mosty is most, or how likely is the conclusion that we're trying to draw in our inductive inference. The second is a qualitative concern that asks us, if, for example, in a statistical syllogism, whether or not there's good reason to suppose that the case in question is an exception to the general rule. We have some confidence concern that has to do with how likely is likely enough for me to take a gamble on believing that the conclusion is true. This kind of comes down to this question of what's on the line. And in a previous lesson, we looked at descriptive statistics to kind of help us get a little firmer handle on that quantitative concern, that how mosty is most question. In that lesson, we saw how we can use the concepts of both central tendency and dispersion to help us get a sense of how representative some statistical value is of a group. We have formal methods for representing a large group through some simple representation in the form of a statistical value in this subdiscipline, this mathematical subdiscipline of statistics. And that subdiscipline is intimately related to another similar mathematical subdiscipline known as probability. The mathematical subdiscipline of probability deals with the formal methods concerning how we can figure out how likely some event is. And so this is going to give us another tool for firming up, kind of like slow thinking and formally thinking through that question about how mosty is most, that quantitative concern that is always looming over us whenever we're trying to think inductively, whenever we're trying to make a likely inference. Specifically in this lesson, we're going to be talking about theoretical probability. And by that I mean how we can think about the likelihood of events even when we don't really have any evidence about what's going on. Oftentimes with statistics, we're trying to figure out how to represent a data set in a simple way. And that's like this question of how it is that I can represent my evidence in a simple way. But with theoretical probability, we can answer questions like this one: what's the probability of flipping heads on a fair coin, even if I haven't collected any data on this coin just yet? And that's because in order to figure out what the probability of flipping heads on a fair coin is, all I need to do is take the number of satisfactory outcomes and divide it by the number of possible outcomes. What I mean by the number of satisfactory outcomes here is how many different outcomes there are that will count as flipping heads on a fair coin. And it seems like there's only one. There's one way to get heads on a fair coin. It's if the coin comes up heads. The number of possible outcomes, though, is 2, because we could have a heads or we could have a tails. And if we say that that the coin that we're flipping is a fair coin, what we're saying is that each of those 2 outcomes is equally likely. So the probability of flipping heads on a fair coin is 1 over 2, 1/2, or 50%. And through this same general principle of dividing the number of satisfactory outcomes by the number of possible outcomes in order to find the theoretical probability, we can look at more complex systems than a fair coin. We can look at something like a fair die that has 6 sides, And each of those sides, if it is a fair die, is equally likely to come up when I roll it. And we can answer a question like, what is the probability of rolling 6 on a 6-sided die? That would be the number of satisfactory outcomes divided by the number of possible outcomes. And there's only one way to roll a 6 on a 6-sided die. It's if the 6 face ends up facing up. And there are 6 possible outcomes. It could be 1, 2, 3, 4, 5, or 6. So 1 divided by 6, or 16.66 repeating percent, is the theoretical probability of rolling a 6 on a fair 6-sided die. Things get just a little bit more complicated if I'm dealing with an OR statement. Remember that OR operator that we saw back when we were looking at formal deductive methods. I could ask a question like, what is the probability of rolling a 2 or a 6 on a single 6-sided die roll? And for that, we just have to kind of recognize that 2 could satisfy my outcome. I'm looking to roll a 2 or a 6. And, well, what's going to make that true? What's going to be a satisfactory outcome? Well, 2 would work, or 6 would work. Remember, as long as at least one of the 2 disjuncts is true, my whole disjunction is going to be true. So 2 will be a satisfactory outcome, and 6 will be a satisfactory outcome. So when I divide the number of satisfactory outcomes by the number of possible outcomes, I need to make sure that I count both 2 and 6 as satisfactory outcomes. And so this probability is going to be 2 divided by 6. I have a 2 and 6, or a 1 and 3, or an approximately 33% chance of rolling a 2 or a 6 on a single 6-sided die. And if you've studied this sort of thing in a math class, you've probably learned a mathematical or an arithmetic formula in addition to this kind of probability tree approach that I'm mapping out here. And that amounts to recognizing that when I'm dealing with an OR statement, what I'm doing is I am adding the 2 individual probabilities of my 2 disjuncts. So there's a 1 in 6 chance of rolling a 2, there's a 1 in 6 chance of rolling a 6. What's the probability of rolling a 2 or 6? Well, just add those 2 things together and you will get the combined probability, or the probability of the disjunction. So let's practice this one more time with another OR statement. Let's look at something that's actually, it's not immediately evident that it's an OR statement. This is a little bit of a buried OR statement. This question asks, what is the probability of rolling an even number on a single 6-sided die roll? Well, even though we're not explicitly using the word or, an even number could be satisfied by lots of different possible outcomes on a 6-sided die roll. 2 would count as an even number, 4 would count as an even number, 6 would count as an even number. So 2 or 4 or 6 is what I'm looking for when I'm looking to roll an even number on a single 6-sided die. So when I divide the number of satisfactory outcomes by the number of possible outcomes, I need to make sure that I count each of those, and that means that I have a 3 in 6 chance, or a 1/2, or a 50% chance of rolling an even number on a single 6-sided die roll. And this probably isn't telling us anything that we don't know already. It's just identifying that we have a formal method of figuring this out. And again, if you prefer to approach this in a more arithmetic way, we can think about this in terms of adding up the individual probabilities of each of the outcomes that would satisfy. Now, it probably doesn't blow your mind that there's a 50% chance of rolling an even number on a single 6-sided die roll, or that there's a 50% chance of flipping a heads on a fair coin. But these are relatively simple systems, and the principle that we've explored, this kind of formal method of figuring out what the probability is the sort of thing that could be helpful in more complicated scenarios where it isn't quite so intuitive what the probability of some event is going to be. And if we can use OR statements with our probabilities, we might also be thinking, oh, can we use some of our other operators like AND? Yes, we can. We have AND statements sometimes, like what is the probability of tossing 2 heads on 2 independent coin tosses? That is to say, I flip a coin and I get a heads, and then I flip the coin again and get a heads again. So how likely would that event be? And I can figure this out theoretically in the same way that I did before. Let's start by approaching it with this probability tree approach. We can recognize that, okay, so I'm going to make one toss, and in my first toss, I have 2 different possibilities, 2 timelines that can kind of be sprung from that first coin toss. That first coin toss could go heads or it could go tails. And there's a 50% chance that it goes either way. Now, when I go to make my second toss, I need to recognize that I could be making my second toss in the possible world where I got heads on the first toss, or I could be making my second toss in the possible world where I threw tails on my first toss. So when I'm thinking about this, I should recognize that, okay, so what's going on here is that every time I throw the coin, I split my possibilities into two. So on the first toss, I split my possibilities into two possible worlds, one where I throw heads, one where I throw tails. And then my second toss could be the one where I threw heads first and then heads again, or it could be the one where I threw heads first and then tails on the second toss. Or it could be a world where I threw tails first on the first toss and then heads, or it could be where I threw tails first and then tails on the second toss. So we can represent that by saying in this outcome we have heads heads, in this outcome we have heads tails, in this outcome we have tails heads, and in this outcome we have tails tails. And from here, we can recognize that we can use the same basic principle of using the number of satisfactory outcomes divided by the number of possible outcomes to find the probability of some event. In the scenario that we're asking about in this question, we have one satisfactory outcome out of 4 possible outcomes. So that means that there is a 25% chance of throwing 2 heads in a row on 2 independent coin tosses. And again, if you've encountered this sort of material in a more mathematical disciplinary context, you've probably also learned that you can multiply the individual probabilities on each independent coin toss. So there's a 50% chance of throwing heads on the first coin. There's a 50% chance of throwing heads on the second coin. And if I want to know the union or the conjunction of those two probabilities, if I want to know what the probability of both of them happening is, then I need to multiply those individual probabilities. And if I can do probabilities with or statements, and I can do probabilities with and statements, we can also probably start to get a sense that I can combine those. That's a thing that I can do with these logical operators. I can make very complex statements that combine multiple logical operators. So if I was asking, for example, what the probability of tossing exactly 2 heads on 3 independent coin tosses, then I might actually have to combine both those and or resources. On my first toss, let's recognize, okay, I'm making 3 independent coin tosses. On the first toss, I split my possible worlds into 2. There's a world where my first toss yields heads and a world where my first toss yields tails. On my second toss, I split those again, so now I have 4 possible outcomes, the heads heads, the heads tails, the tails heads, and the tails tails outcomes. And then we do a third toss, which is going to split each of these into again. So I have the heads 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 world, I have the heads heads tails world, I have the heads tails heads world, the tails 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 world, etc., etc. And what we're looking for here is what the probability of throwing exactly 2 heads on 3 independent coin tosses is going to be. So that means I'm looking for all of the outcomes with exactly 2 heads. This one has 3 heads. That's too many heads. I'm looking for exactly 2. This outcome satisfies, this outcome satisfies, this outcome satisfies, but none of the rest do. We have 2 times 2 times 2, 8 possible outcomes, and 3 of those outcomes satisfy the conditions that I'm looking for. So if I want to know the probability of this, then I divide the number of satisfactory outcomes by the number of possible outcomes. In this case, that is 3 divided by 8. Or, put differently, I have a 37.5% chance of throwing exactly 2 heads on 3 independent coin tosses. And if I wanted to change this question just a little bit, if I wanted to loosen up my conditions for getting a satisfactory outcome, and instead of saying exactly 2 heads, I said at least 2 heads, then we recognize that, okay, well, this outcome, this first outcome, is now going to be satisfactory. Let's see, are any others going to become satisfactory? Nope, that's not at least 2 heads. That's not at least 2 heads. That's nope, nope. So yeah, we would have 4 out of 8, or a 50% chance of throwing at least 2 heads on 3 independent coin tosses. Let's practice that one more time, just in case there are some folks who are still having trouble kind of getting the hang of how we approach these sorts of questions. Let's say I flip a fair coin and I roll a 4-sided die. So this is going to be even more complicated now. I have both coins and dice in the mix. So one coin toss, one four-sided die roll. Not a six-sided die this time, a four-sided die. What is the probability of rolling a heads and a four? And as a separate question, what's the probability of rolling heads or a four? Okay, all right. I think we're up to attacking these sorts of questions. We'll recognize that we have one coin toss that splits us into two possible worlds. And then after that coin toss, I have a die roll, a four-sided die roll, that's going to split each of those worlds into four. So I have the possibility of heads then one, heads then two, heads then three, heads then four, tails then one, tails then two, tails then three, and tails then four. And those are all of the possible outcomes of a fair coin flip and a four-sided die roll. And if I want to know which of these are going to be satisfying the conditions that I'm looking for, I just have to recognize that my OR statement has different conditions than my AND statement. My OR statement's a little bit more permissive than my AND statement. For my AND statement, they both need to be true. It needs to be heads and four, and that only happens in this outcome. Only once out of the 8 possible outcomes do I get heads and four. And if I'm looking for heads or four, well, that's a lot more permissive. I just need at least one of the two to be true. So that satisfies, that satisfies, that satisfies, that satisfies. And then down here, this one that I have tails and four, that one satisfies as well. So again, for heads and four, my probability is just going to be the one satisfactory outcome out of the 8 possible outcomes. And for my probability of heads or four, we have a much larger probability of 5 satisfactory outcomes out of 8 possible outcomes. And we can even bring these same sensibilities into a question that looks a lot more complicated, like this one where we've got a bag containing a whole bunch of different objects: green cubes, yellow spheres, orange spheres, green tetrahedra, and orange cubes. And I'm trying to figure out the probability of pulling an object at random out of this bag. I can do that, and I can do that even if I have complex expressions or complex conditions for what's going to be a satisfactory outcome. I won't work through this one because this is one of the questions that you have on your homework assignment. But I will note that this gets even more complicated, and I think more complicated than we'll go into in this lesson, more complicated than a critical thinking class really demands, by noting that we can not just talk about one object being pulled at random out of the bag, but I can then ask questions about, okay, well, what if I pull a second or a third or a fourth object out of that bag as well? And those probabilities are going to be even more complicated than the kinds of scenarios that we've just been looking at, because each time I remove an object from the bag, I'm taking it out of the world of possibilities. So if I pulled a green cube out on the first turn, that's going to lead to a very different set of possible outcomes that could happen on the second draw compared to if I had pulled a yellow cube out on the first draw. I need to recognize that every time I remove some object from this bag, I'm changing the theoretical system that I'm trying to explore here. That's not the case with flipping a coin or rolling a die over and over and over again, because a coin toss is a 50-50 chance for heads or tails every time I flip it. The history of the coin doesn't really matter to the future of the coin, the way that the history of this system is going to matter to the future of that system as I continue to pull objects out of the bag. So that's one direction that we can think of that these kinds of scenarios could get a little bit more complicated, but the general principle of dividing the number of satisfactory outcomes by the number of possible outcomes is essentially going to be the same. But what about questions kind of like these questions? Let's say that you're at a carnival and you come up to a booth, and this booth has 2 games. One of these games is called Big 12 and the other one's called Lucky 7. And we're wondering whether one of these games is a smarter bet than the other. In addition to comparing the 2 games, we might even wonder whether either game is worth playing. In Big 12, the rules of the game are like this. You're going to roll 2 6-sided die, and if you roll a 12, then you're going to win $24. If you don't roll a 12, you lose $1. That's why it's called Big 12. If you get that Big 12, you get a big payoff of $24. But anything else besides that Big 12, you're going to lose the $1 that you're putting up to bet. In Lucky 7, you have a slightly different game with slightly different Outcomes, here we're going to roll two six-sided dice, and this time if I roll a 7, I'm going to win $7, and if I don't roll a 7, I'm going to lose $1. So again, is one of these games a smarter bet than the other, or are either of these games worth playing? Well, this is a slightly different sort of a question than the questions that we have been looking at, because something new has come into the mix. We're no longer only talking about how likely these events are, we're also starting to take into account what there is to lose and what there is to gain based on the probabilities that we're wondering about. This is a question that we've noticed is always lurking in the background of any likely inference or any inductive inference, this question of whether likely is likely enough to take a chance on. And we've noted in previous instances that we've come up against this question that part of answering how likely is likely enough involves asking what's at stake if we're right, what's at stake if we're wrong, what there is to gain in playing this game versus what there is to lose in playing this game. In probability, we refer to this combination of the concept of likelihood with this question of what's on the line with the concept of expected value. Expected value tells me what I can expect to gain or lose if I take some probabilistic chance over and over and over again in the long run. Arithmetically, what we do to calculate expected value is we take the probabilities of each of the possible outcomes and we multiply that probability by the value of that outcome. That is to say, we give it weight according to how much we would win or how much we would lose. If I'm winning something, then this value is going to be positive. And if I'm winning something big, it's going to be a large positive value. And so I want to give that outcome a little more weight because it represents a big payoff if that outcome happens. If the condition that I'm wondering about is a losing condition, then the value is going to be negative. It's going to be something that is lost. And if it's losing a lot, it's going to be a large negative value. And so we'll see that for each of these terms in the calculation of expected value, all I'm really doing is I'm weighting the value of each outcome according to its probability, or perhaps thought in a different way, I'm weighting the probability according to the value of the outcome, and then adding all of those up. So let's approach this question. Say I bet $1 that I'll roll a 6 on a single roll of a fair six-sided die. And we're wondering, kind of like we were on those other more complicated games, is this a game that I want to play? What's the expected value of playing this game over and over and over again? If I play it just once, I'll either win or I'll lose. I'll win $1 or I'll lose $1. But what I'm trying to get a sense of when I'm wondering what the probability of winning or losing is what do I think would tend to happen if I played this game over and over and over and over and over again? Well, in the long run, all of the wins and losses will kind of like average each other out, and I can begin to talk about how much is gained or lost on average each time I play the game. And that's essentially what expected value is telling me. Okay, so the expected value, again, is going to be the likelihood, the probability of winning times the value of winning, and we're going to add to that the probability of losing times the value of losing. And for the scenario that we're talking about, we have a single six-sided die that we're going to roll, and we're looking for my win condition here. My satisfactory condition is to roll a 6. Every other outcome is going to be a losing condition. So we have a 1 in 6 probability of winning. That is to say, to roll a 6 on a single six-sided die, a 1 in 6 chance of that happening, and I will win $1. So the value of that outcome is 1. And I'll add to that the probability of losing, which is 5 in 6. All of these other outcomes are my satisfactory outcomes for the lose condition. And so that's 5 out of 6 outcomes times what would be lost. What's the value of this outcome? And that is -1. I would lose $1 for each of those 5 possible outcomes. With a little bit of arithmetic number crunching, this comes to an expected value of -66 per play. That is to say that over the long run, if I keep playing this game over and over and over again, I can expect to lose 66 cents each time I play the game. Now, maybe that means it's not a good game to play. It certainly seems like it's only a good game to play if what you intend to do is lose money. You can expect to steadily lose money as you continue to play this game. But maybe you would look at this game and think to yourself like, well, it seems like 66 cents worth of fun for each time that I play it. And if that's what's going on, then yeah, maybe it would be worth it. It's worth noting here that the values of what's lost and gained each time here is really only referring to the money that's won or lost. And it's at least one possible criticism of approaching expected value in this way, that it might tend to force you into thinking about ways that you can precisely quantify what is won and lost. And in a hypothetical scenario like a gambling scenario, these games of chance that we're looking at in this lesson, it's relatively easy to figure out what's won or lost. But it is true that in real life scenarios, trying to place a precise numerical value on what is won or lost in some probabilistic outcome is not always that easy to do. All right, so let's try another scenario just to get a little bit more practice with expected value. Let's look at a scenario where I've got a similar game. I'm going to roll a single six-sided die, and the win condition is that I roll a six, and anything else is going to mean that I lose. But this time, instead of it being a straightforward $1 bet that, I'll lose $1 if I don't roll a six and I'll win $1 if I do roll a six, let's make the payoff a little bit bigger. Let's say I'll win $3 if I roll a six. Again, my approach is the same. It's the probability of my win condition times the value of my win condition plus the probability of my lose condition times the value of those lose conditions. And in this case, what I'm going to end up with is still that it's a losing game, but I'm losing less each time that I play. And that makes sense. I've kind of increased the payoff for winning. So with this slightly altered version of the game, I can expect to lose 33 cents for each time that I play. And again, if it's 33 cents worth of fun each time I play, maybe that's worth it. Maybe that means that I'll play it. But I can be expecting to lose money. And this raises an interesting question of how much would I have to win in order for this to start to not be a losing prospect? How much would I have to win in order to break even in the long run? Well, I think we can kind of spot in the equation what's going on here, that like my lose condition is always a 5 and 6 chance, and the value of losing is always -1. So what I'm looking to do in order to break even is to have something in this term that counterbalances what I'm losing in this term. So I would need to come out to a $0 or 0 cents won or lost each time that I play. And that means that this term would have to be 5 divided by 6, which means that the payoff would have to be $5. At $5 won for every time that I roll a 6, this will be a game where I can break even. And for $6 won for rolling a 6, this starts to become a game where I can expect to win money in the long run. Frequently in gambling scenarios and other sorts of games of chance, this is exactly what's done in order to make things more interesting. We take an outcome that's very unlikely, but we give it a much higher payoff than the more likely losing outcomes. And that kind of makes the scenario complicated enough that we're not as sure what's going to happen, and it makes the experience a little bit more fun. And it's all well and good to have fun with these games, but we also probably need to recognize that, especially with things like gambling, those complications can prey on our inability to think carefully and critically about probabilistic scenarios. So let's return to those two carnival games that kind of sparked us off wondering about expected value, this way of combining the likelihood of an outcome with what's on the line. So we get like two of our concerns about inductive inferences satisfied at once, both the quantitative and the confidence concern. The first of those games, remember, was Big 12. The second was Lucky 7. And we were wondering, is one of these games a smarter bet than the other? And is either game worth playing? Let's take a look at Big 12 first. Should we play this game? Okay, so we're rolling two six-sided die, or two six-sided dice. And that means that there are going to be 36 possible results, because the first die has a explodes into 6 possible worlds, and each of those 6 possible worlds explodes into 6 more possible worlds on the second roll of the die. So that's 36 possible outcomes whenever I roll 2 6-sided dice. And when I recognize that the win conditions for Big 12 is that I roll a 12, I gotta recognize that the only way to roll a 12 is to roll 2 6s. That's what I'm looking for when I'm looking to roll a 12. Only one of these possible outcomes in the 36 possible outcomes gives me a total of 12. That would be the double 6. So when I'm looking for the expected value here, I need to recognize that I have a 1 in 36 probability of winning and a 35 in 36 probability of losing, and that's what's being stacked up against the $24 value of the win condition versus the $1 value of the lose condition. So we plug all of that into our equation of probability of winning times value of winning plus probability of losing times the value of losing. That gives me 1 in 36 chance of winning, but a $24 positive value for winning, plus a 35 in 36 chance of losing times a -1 value. That is to say, I lose $1 if this is my outcome. And that comes to still a loss. The expected value of playing this game over and over again is that I will lose 30 cents for each time that I play it if I play this game over and over and over and over again in the long run. In any one particular time that I play it, I'm either going to win $24 or I'm going to lose $1. That's going to be the outcome. But the average outcome in the long run, if I played this game over and over again, that is to say, the theoretical expected value of playing this game is going to be a 30-cent loss for each time that I play it. And that seems to suggest that I should not play this game. This game is not a smart bet. Unless, as we've been saying before, unless it's 30 cents worth of enjoyment for each time you play it as well. That's, this added value that's going to be present whether you win or lose. Well, maybe Lucky 7's a better game. Let's take a look at that one. In Lucky 7, again, we're rolling 2 fair 6-sided dice, and the win condition here is instead of a 12, it's a 7. And that's a way easier outcome to satisfy, but also at the same time, I'm not winning as much when I hit it in Lucky 7. So should I play this game? Well, again, 36 possible outcomes for rolling 2 6-sided dice. And when I try to think of all the ways in which I can satisfy that win condition of rolling a combined value of 7, I need to recognize that it matters whether I'm talking about the first die being a 1 and the second one being a 6, or the first die being a 6 and the second one being a 1. Those are 2 different possible worlds. Those are 2 different outcomes. So there are 36 possible outcomes, and one of those possible outcomes is a 1 and a 6, and another possible outcome is a 6 and a 1, and those are 2 outcomes that both give me a 7. There's also the outcome of a 2 and a 5 and a 5 and a 2, so that's 2 more for a total of 4 so far. And then there's 3 4 and 4 3, so 6 total possible ways of getting a 7. All right, so let's crunch this out. Again, the expected value is the probability of winning times the value of winning, plus the probability of losing times the value of losing. We were just figuring out what the probability of winning is. It is 6 outcomes out of 36 possible outcomes, so 6 and 36. The value of winning is $7. The probability of losing is everything that isn't one of my win conditions. So if there were 6 out of 36 possible outcomes for winning, there are going to be 30 out of 36 possible outcomes for losing, and each of those is going to have a value of -$1. That comes out to a positive number. I can actually expect to win money on this carnival game. This carnival can expect to lose money on this game, and everybody who plays it can expect to win money. If you are sharp in the way that you can think critically about probability and expected value, you would be able to recognize that this is a game that you could make money at. So you should play it. Unless, again, what you're seeking out to do by playing this is to lose money. I don't know, maybe this is a carnival that's at a fundraising event and you actually want to give your money to the people who are running the carnival and you don't want to take the money away from them. Then maybe you don't play this game. But But the point still stands. You can expect to win 33 cents each time you play this game over the long run. And again, that's on average. That's a theoretical value. You're never actually going to win 33 cents anytime you play this game. You're either going to win $7 or you're going to lose $1. But over the long run, if you played it over and over and over again, each of those plays would average out to positive $0.33 per play. And that's what we mean by the theoretical expected value. All right, let's look at one more scenario that I think is probably the most complex one that we've seen yet. This is another carnival game. It's a carnival game where you're throwing a dart at a grid of 40 balloons to win a prize. And there are 3 kinds of prizes that you can win. You could win a small prize, a medium prize, or a large prize. And what we can assume in this game is that you're definitely going to hit exactly 1 balloon with any throw that you make. Let's say that 20 of the balloons in this grid are going to yield a small prize. 15 of those balloons are going to yield a medium prize. The large prize ones are like a lot more rare. There are only 5 of those balloons. It costs $2 to play this game. And again, assume that you're definitely going to win some sort of prize because like you're definitely going to hit exactly 1 of these balloons in this grid. So for $2 to play, you could maybe win a small prize, maybe win a medium prize, or maybe win a big prize. The small prizes, by the way, are worth 50 cents. The medium prizes are worth $1.50, and the large prizes are worth $6. Is this game worth playing? Well, we can figure this out with all of the tools that we've been developing in this lesson. So let's think about what each of the possible outcomes in playing this game is. There's one possible outcome where I win a small prize. So in that outcome, I spent $2 and I gained 50 cents, and that means that I got a net loss of $1.50 for that outcome of playing the game. It's also possible that I might win a medium prize, and if that happens, then I spent $2, but I gained $1.50, or I gained a prize worth $1.50. That's still a net loss, but it's a smaller net loss. It's a net loss of 50 cents. And then there's the big win. There's if I get the large prize. If I get the large prize, then I spent $2 and I gained something that has a value of $6. And so it seems like I have a net gain of $4 for that outcome. And if I want to figure out the expected value for playing this game, again, I need to recognize that I'm talking about the probability of one outcome times its value plus the probability of all the other outcomes plus their values. This one's a little bit more complicated in this scenario because I don't just have winning and losing. In every outcome, I'm losing something, I'm spending something, but I'm also gaining something. So I have 3 possible outcomes to worry about here. There's the possible outcome of the small prize, of the medium prize, and of the large prize. The probability of getting the small prize is 20 out of 40. There are 20 balloons out of the 40 total balloons in the grid that will give me the small prize. And the value of that outcome is negative 1.5, or negative $1.50. The probability of my medium prize is 15 out of 40 times negative 0.5. That's the value that would be lost by spending $2 and gaining a prize worth $1.50. And the probability of the big prize is only 5 out of 40, but its value is quite large. It's something of equivalent value to $4 when this outcome obtains. That shakes out to an expected value of negative 0.4375, so I can expect to lose approximately 44 cents each time I play this game. So essentially that means that big payoff on the big prize isn't big enough to make up for how unlikely it is that I'll get that big prize. And maybe this means that I don't play this game because I recognize that it's a way of losing money, but then again, as we've been saying, maybe I also think to myself, the game is fun, and it's, maybe 43 cents worth of fun, or 44 cents worth of fun for each time I play it. But you can also see how this is the sort of thing that you could make money at. If you were running this booth, if you were running this game, you could just kind of sit back and let people have 44 cents worth of fun over and over and over again, and steadily the money would come in. So as I noted before in the descriptive statistics lesson, this is just the tip of the iceberg. This is really, a philosopher who's teaching critical thinking's approach to probability. If you want to really get into the formal methods that are involved in working through theoretical and experimental probabilities, you should take a proper probability class in a math department. Or you could explore the many free resources that are available for math instruction on the internet, including here on YouTube. I hope this lesson has been a useful and effective introduction to the idea of using formal mathematical methods in order to determine how likely some event is and what's on the line, and at the end of the day, whether or not I should believe the conclusion of some inductive argument. I look forward to seeing you in another lesson.